The type of fuel injection system usually used on aircraft piston engines is the low-pressure, continuous flow type of indirect fuel injection. Although this type of system is fuel inefficient, it does eliminate the need for complex injection timing devices and spring-loaded injector nozzles. The price that's paid for the simplicity of the system and its relatively trouble-free operation is the comparatively inefficient way in which it uses fuel. In this type of system, fuel is sprayed continuously into the induction port as close to the inlet valve as possible, as is shown in this diagram. The advantages claimed for the method are low operating pressure, good fuel distribution, freedom from icing problems, and the ability to use a pump which does not have to be timed to the operating cycle. Some fuel injection systems operate on a similar principle to the carburetor, but inject fuel under pressure into the intake. In the indirect injection system, a throttle metering valve varies the pressure of fuel according to airflow to the engine. Mixture strength is varied by a manually operated mixture control valve, which adjusts the fuel pressure for altitude or operating conditions as necessary. This same valve is also used to cut off the fuel supply when stopping the engine. Because of the method of operation of the injector, no special idling arrangements are required, and a separate priming system for engine starting is usually unnecessary. The main components in the system are a fuel pump, a fuel air control unit, a fuel manifold or distribution valve, and discharge nozzles for each cylinder. In addition, a normal throttle valve controls airflow to the engine, and a fuel pressure gauge is fitted to enable mixture adjustments to be managed. The system is normally equipped with two fuel pumps, an engine-driven one and an electrically operated one, which are arranged in parallel. Because of the parallel pump arrangement, when the engine-driven pump is not operating, fuel under positive pressure from the electrical pump can flow independent of the engine-driven pump. This allows the electrical pump to be used in case of a malfunction of the engine-driven pump and for engine priming and starting. The fuel air control unit is mounted on the intake manifold and contains the air throttle assembly, the throttle valve, and two valves which control the fuel flow to the engine. First, the mixture control valve, and secondly, the throttle metering valve, sometimes called the fuel metering valve. The air throttle assembly contains the air throttle valve, which is connected to the pilot's throttle lever and controls airflow to the engine. Note that in this type of system, no venturi is required to suck fuel into the airstream. Thus, the chances of encountering icing problems in the inlet manifold are much diminished. The first valve that the fuel encounters as it passes through the fuel air control unit, the mixture control valve, is connected to the pilot's mixture control lever and bleeds off fuel pressure which is being applied to the fuel metering valve. Thus, the air-fuel ratio can be varied from the basic setting of the fuel metering valve as required by operating conditions. The mixture control valve can also be closed off completely, thus acting as the idle cut-off control. The second of the two valves which control the fuel flow into the engine, the fuel metering valve, is mechanically connected to the throttle butterfly. It controls the flow of fuel coming from the mixture control valve according to the position of the throttle butterfly. Thus, fuel flow to the manifold valve, and subsequently the injectors, is proportioned to airflow. The fuel manifold valve is located on the engine crankcase. It's the central point for distributing metered fuel to the engine. When the engine is stopped, all the outlet ports are closed, and no fuel can flow to the engine. As fuel pressure builds up, as a result of engine rotation or booster pump operation, it pushes upwards on a diaphragm, allowing all the ports to the discharge nozzles to open simultaneously. The diaphragm ensures that the ports are fully open before fuel starts to flow. When the inlet fuel pressure drops below a certain level, for instance at engine shutdown, The diaphragm closes the fuel inlet, which shuts off all the fuel to the discharge nozzles. This stops both vapour locks occurring in the delivery line and the engine running on when idle cutoff is selected. At the same time, it ensures that fuel pressure is available instantly the next time the engine is started. A fuel discharge nozzle is located in each cylinder head, with its outlet directed into the inlet port. Nozzles are calibrated in several ranges, and for best results, in both economy and engine power, are fitted to individual engines as a set, each nozzle in a set being calibrated for its particular position on the engine. Normally aspirated engines use a nozzle equipped with a fixed calibrated orifice, which has a series of holes drilled just below the orifice chamber for air entry to the lower chamber. A screen and a stainless steel shroud covers this part of the nozzle. As fuel passes through the calibrated orifice to the lower chamber, ambient air is pulled under the shroud and through the screen, finally mixing with the fuel as it's sprayed into the intake port. Nozzles used in turbocharged engines are slightly different in arrangement, but operate in exactly the same way as those used in normally aspirated engines. Instead of mixing ambient air with the fuel, turbocharger output air is delivered to a shroud surrounding the nozzle and forced into the injector to assist in atomizing the fuel spray. It's generally accepted that the fuel injection units used on the engines used in most light aircraft do not need heated air for the purpose of induction venturi icing protection. However, it has been suggested that operators should consider incorporating an alternate air door as a means of preventing manifold air starvation caused by filter blockage from icing or other ingested materials. The intention of this design is that when a pilot first encounters flight conditions where foreign materials, including snow and freezing rain, might be ingested into the induction air system, he should actuate the alternate air door. This will shut off the ram air inlet and, at the same time, admit unfiltered air from inside the cowlings directly into the injector airbody throat. This concludes the lesson on fuel injection.